Hey there, chemists. In this lesson, we're going to look at how we use X-ray diffraction to determine properties of things based on using crystals and how X-rays interact with crystals. To start off, we need to talk a little bit about how to speak wave. We're going to be talking about wavelengths of X-rays, so I just want to recap a couple of terms that we should all be familiar with. Here is a picture of how a wave can be represented in the electromagnetic spectrum. Some terms you should be familiar with. The peak of any wave is referred to as a crest. Down here at the bottom, you have what's called a trough of a wave. The height of a wave, this part here is the amplitude. Sometimes abbreviated with the Greek letter psi, P-S-I, which looks like that. And then the most important part that we'll use here, from trough to trough or crest to crest, or really just one full cycle of a wave, is called the wavelength. And we've seen that before. And that's abbreviated, for the most part, with the Greek letter lambda. So, what are we talking about waves for? Well, when you have multiple waves, you've no doubt learned in your physics class that you can get different kinds of interference. And there's two types that are of most significance to us. There's constructive interference. That's when you have waves that are in phase, and the peaks on one wave perfectly match with the other. They're perfectly in phase. And what you get is a constructive interference. They actually add together. So I'm going to simulate that with a wave that simply has a much larger amplitude. In fact, that's the point. The amplitude doubles. You could say it's noisier. Contrast that with destructive interference. That's the exact opposite. They're exactly out of phase, and the waves more or less cancel each other out, so you get no signal when you have a destructive interference. And this brings us to detecting what's called an interference pattern when we look at how specifically X-rays interact with planes in a crystal lattice. So this is what X-ray diffraction is all about. X-ray diffraction occurs, I'm just reading here, when beams of light scatter from a regular array of points, such as a plane inside a crystal, like we talked about in the last lesson, in which the spacing between the components are comparable wavelengths of light, and X-rays have wavelengths that are on the scale of atomic distances. So we use X-rays because their wavelengths are down on the scale of how far apart atoms are. So this gives us a way of actually measuring wavelengths of X-rays and correlating that with distances between atoms in a solid crystal. This is done by seeing a constructive interference pattern when waves are parallel, and destructive when they're out of phase. So let me draw what that paragraph is trying to show us. So let's pretend we have a plane of atoms, like one of the planes we talked about in the previous lesson. So there is a plane, and just to remind us, this is of atoms. I'm going to say that it's a plane where the atoms are all in contact with each other. So we'll just draw a handful of atoms right next to each other. Now let's say I have an incident beam of light. So let's draw a beam of light coming in, and it can reflect off of that plane. So here we have an incident beam. And we can control that using X-rays that we generate from a machine that does this. I'm going to label this. I'm going to call this ray 1. And it comes in with some wavelength, but there's never just one plane of atoms. Remember we talked about planes last time, and they can be parallel and are parallel to other planes. So let me actually draw a second plane of atoms right below the first one. Here's just another layer of atoms. We'll say it's a crystal of atoms that are all the same. I'll try to make them circles. There we go. For the most part, you get the idea. As a reminder, your drawing does not need to be perfect. And we have another beam coming in at the same angle. So I'm going to draw another one parallel to this. also being reflected. And I'm going to call that beam 2. Both coming in at an incident angle, let's say theta. Now, ray 2, you can tell, is traveling farther than ray 1. It's actually penetrating that first plane on top and being reflected off of the second plane. So, ray 2 travels farther than ray 1. How much farther? Well, let's zoom in and put a couple more points on this graph here. If we do that, let's highlight a couple of spots. I'm going to actually draw a line perpendicular, or a dotted line perpendicular to each of my rays, and make a couple of triangles out of this to the best of my ability. And we'll call this a point, we'll call that a point, and we'll call that another point. So we have two right triangles with their hypotenuse, their respective two hypotenuses are touching each other. I'm going to label these, let's go one other color here, X, Y, and Z. And it's the sum of segment XY and YZ that are actually the extra distance that ray 2 has traveled. And let's see, remember these are, so the farther distance is segment XY plus YZ. Now we don't measure lengths of light, we measure wavelengths of light. So these are waves, and I'm going to draw waves on top of here. Let's go one other color, just something a little bit exotic. There we go. And if we have, let's say, some wavelength on the incident beam, and then I have another wavelength, same incident beam, it gets as far as X. It's this extra part that's traveling. Now, if that extra part that's traveling happens to give us a constructive interference pattern, then we know the waves have matched up again, and we are off by exactly an integral amount of wavelengths, a whole number amount of wavelengths. So, if, what's the point of all this? If the sum of XY plus YZ is equal to some integral number of wavelengths, we have constructive interference. And that's the whole point. And we see that. This is just a picture of what an interference pattern looks like. It shows us how certain spots are brighter than others. That's actually what an X-ray diffraction pattern looks like. And there are other ways that chemists can look at these and decipher what this means. Right now, it just looks like a grid of spots. But the theory behind this is that if you have an integral number of wavelengths in the difference, you get an interference pattern that we can actually use. So how do we use this? If you didn't like your drawing up above, fear not. Here is one already provided for you. That's a much better version that I borrowed from one of your textbooks. And it says, consider two in-phase waves being reflected by atoms in two different layers of a crystal. That's what we were just attempting to draw up there, so this is just recapping it. Solve for the distance, d, between the two layers in the crystal in terms of the wavelength and the number of wavelengths. So I'm going to zoom in on one of these triangles right here. Let's just look at that. And notice the incident angle, which we can control when you point an instrument at a crystal. That's going to be equal to this angle theta there. And if we apply a little bit of trigonometry, and I say the sine of that angle, theta, well, if I remember SOHCAHTOA, that's opposite over hypotenuse. So that's the segment xy divided by, the hypotenuse is d. That's what we're actually trying to solve for. Well, xy is half of that extra length, that extra distance that wave 2, or ray 2, is traveling. So xy is half of the integral number of wavelengths, and n is just some positive integer divided by d. Now you rearrange and we solve for d, And you get that the distance is the integral number of wavelengths times the wavelength divided by 2 times the sine of the angle theta. All of that was just to derive that equation. This is called Bragg's law. This was developed by actually a father and son team jointly who won the Nobel Prize in 1915. So it is sometimes called Bragg, singular, possessive law, but it's also correctly sometimes called Braggs's law, since it was done by two Braggs. Imagine getting your Nobel Prize with your father. That's someone who's really dedicated to their work. So let's just close out with practicing this. Let's say we have X-rays that we can control at 1.54 angstroms. They're used to analyze a crystal of aluminum. Reflection was produced at 19.3 degrees, and that's the idea. You basically adjust the angle and the wavelength. Those are things that we can control with an instrument until we see this interference pattern, and we know we're getting a constructive interference with an integral number of wavelengths. Solve for the distance. So d is equal to n lambda over 2 sine theta. N, they're telling us, is 1. Lambda is 1.54 angstroms. That's a capital A with a little o above it, divided by 2 times the sine of the angle, 19.3 degrees. You plug that into your calculator, you get 2.33 angstroms. Maybe you haven't seen an angstrom before. An angstrom, 1 angstrom, is 10 to the negative 10 meters. It's often used when we're describing bond lengths and things like that. They ask it for us in picometers. So if I had to convert that to picometers, this becomes 233 picometers. Remember, a pico is 10 to the negative 12. Okay, so that's how we use properties of crystals and X-rays specifically in a technique called X-ray diffraction to get properties on atomic scales, namely in this case, how we get the distances that separates atoms in a crystal structure. And we'll go forward with this and learn how we can actually use this to figure out what the crystal packing pattern is. That's where we started. Is this simple cubic? Is this face-centered cubic? And it is related to this technique.